So this is a non-inverting op-amp, and it looks like this. This is 3.2 volts. This is the non-inverting. This is the inverting. This is R1, and it's 47K. This is R2, and it's 22K. This is our V out. So 3.2 volts is our V in, and we need to calculate voltages and currents. Okay, so the first thing we want to do is the golden rule of op amps is that the inverting and the non-inverting inputs are equal. And the second rule is that the current in the inverting is equal to the current in the non-inverting, which is equal to 0. Okay, so we're going to start with number 1, and we're going to match the voltages going into the inputs. So we're going to call this point right here A. So we know that VA is equal to V non-inverting, which is equal to 3.2 volts. And since if this is 3.2 volts here, then I know my current is going to be flowing to the left. So I is going to be flowing this way because this voltage here is higher than ground here. So I can find, so that's what I'm trying to find. If I find the current I know there's I equals 0 here. So I know that the current through R1 is the same as the current through R2. So let's solve for I. So I is going to equal the voltage drop across R1. So that's 3.2 volts. Let's do the equation first. So we're going to say V at A minus 0, because that's the ground, over R1. And so that's going to equal 3.2 volts minus 0 over 47K. And so I then is equal to 68 microamps. So if that's true across R1, then that's going to also be true across R2. So if we want to calculate the voltage drop, so the voltage drop across R2, so we can say the voltage drop across R2 is going to equal the current times the resistance of R2. So that's going to equal 68 microamps times 22K, and that will equal 1.5 volts. So if I know my current is flowing to the right, then I know I have 3.2 volts at A, then my V out is going to equal the V across R2 plus VA. So if I'm dropping current as I move from V out, I'm saying that V out is minus the voltage drop across R2 minus the voltage drop. So this is V out is the voltage drop across here, the voltage drop across R1 to get to 0. So I can go backwards and add them up to get to V out. So I know V out has to be, because current is flowing from left to right, V out has to be at a higher voltage than VA. So I can say then that V out is equal to 1.5 volts plus 3.2 volts equal to V out. And that V out then is equal to 4.7 volts. So we've calculated the currents that we needed through R1 and R2, and we calculated the voltages at each of the locations and the output voltage. The other good thing to check here is that this is a non-inverting op-amp. And how do I know that? And I know that because the signal here, this voltage is considered my signal. It can be a DC voltage in this case, like a battery, but we could also have a time varying signal that would look like this on the input. So to see where the input is on whether it's a time varying or a DC value, what input it's going to. And so here it's going into our non-inverting op-amp. And if that's the case, we know that our non-inverting op-amp, it should have a positive V out. And so most of the time that means that our V out is going to, the current is going to flow this way through the resistor.